Okay, so welcome to the next discussion. What we're going to do today is we're going to talk about the various classes that make up the ForkJoinPool framework, starting with the ForkJoinPool class. And as you'll see, there's a number of methods that are interesting here, and we'll talk about them first, and then we'll start diving down into the various constituent elements that are part of the other classes that formulate the different elements in the ForkJoinPool framework. So I think I mentioned this before, the ForkJoinPool class extends the abstract Executor service class, which in turn implements the Executor service interface. And as a consequence, there's a bunch of methods that it kind of gets along the way for doing that. And there are 4 key methods here. We're going to talk about them very briefly, even though it's really outside the scope of this class to talk about this in any detail. So the execute method takes a runnable and arranges to have that runnable executed in a thread in the background as part of the pool and part of the ForkJoinPool. And a runnable is a one-way task, so there's no return value that comes back from that. The submit method, in contrast, submits a two-way task for execution and will return a future. And so you can use this to give a two-way task that'll run in a background thread in the ForkJoinPool, and when that ForkJoin thread is done, then the future will be triggered and you can get the result from the future. The other couple methods here are done on collections. One is called InvokeAll, and it takes a collection of two-way callable tasks, and it goes ahead and runs them, and it waits for them to finish, and what you get back will be all the results that finished, if they finish correctly. And then the final method is the InvokeAny method, which takes a collection of tasks, and it goes ahead and has them all run, and then it waits for the first one to finish, and it cancels all the other ones that haven't finished. So it's just trying to get one result back. As it turns out, we're not going to talk about any of these methods any further because they don't really leverage any of the powerful ForkJoinPool features. Although under the hood, they conceivably could use some of the stuff like work stealing and so on. But we're not really interested in these things for the purposes of our discussion. I'm just including them here for completeness. What we are going to talk about are the methods that are used by so-called non-ForkJoin task clients. What the heck does it mean to be a non-ForkJoin task client? Well, these are basically parts of a program that will invoke operations on a ForkJoinPool that are not calling from the context of a ForkJoin task itself. And that'll become more clear when we talk about what ForkJoin task does. So these are used to get non-ForkJoin tasks to submit ForkJoin tasks into a ForkJoinPool so that they can then run to completion by a thread in the ForkJoinPool. And the way this works is there's a little shared queue here, and when a client calls any of these methods like submit, invoke, or execute, it plops the ForkJoin task onto this shared queue, and then the threads that are running in the worker pool of ForkJoin threads will take those things off the queue and then start to run them. And then from that point onwards, everything will take place in the context of ForkJoin tasks running in the ForkJoin pool. So then now it's ForkJoin task behaviors as opposed to non-ForkJoin task clients. And again, that distinction may seem a little bit odd at first, but it'll make sense when we talk more about what ForkJoin tasks do under the hood. And it all has to do with being able to steal the various subtasks inside the ForkJoinPool. These methods do leverage all the powerful properties of the ForkJoinPool, so they're the really cool things that we want to be able to discuss here. Execute will arrange the execution of a one-way task, and Invoke will perform the task, and so this, notice how when you execute this thing, there is no return value from it. It just executes it. It's a one-way task. It runs in the background. Invoke here will perform the task and block until the task completes, whereas execute does not block. So execute does not block, whereas invoke does block. So it's a two-way call. And then submit is going to submit the task, which will then go ahead and run. And what we get back is a ForkJoin task. And you'll see in a minute a ForkJoin task is a future. So then we could always wait on this thing to finish somehow. And we'll see there's various ways of doing this kind of stuff. Again, this is really just to get things into the ForkJoinPool framework. Once things get into the framework, there's a slightly different programming model that we'll see as we talk about the ForkJoin task itself. The size of a ForkJoinPool, if you just call the constructor here that's the default constructor that takes no parameters, is going to default to the number of cores that are available to the Java runtime. And so in that case, it's going to, under the hood, call runtime.getRuntime.AvailableProcessors, which is a goofy name left over from the days before we had multi-core processors. And so back in those days, you actually had multiple processors, not multiple cores. And so that's why it says available processors. But think about that as being the number of cores. So if you had a 4-core machine, then getRuntime.AvailableProcessors would return 4. Yes, sir? Yeah, great question. So the question is, will this call here, runtime.getRuntime.AvailableProcessors, how does that set? That's actually set by whoever implements the Java execution environment, which could be a virtual machine, which could be a ahead-of-time compiler type of environment like you see with modern versions of Android. And in all cases, it's something that's set by whoever implements the execution environment, like the virtual machine developers. And it would typically, under the hood, go and look at some characteristic that's describable down in the bowels of the system. See, you as an end user cannot set that. It comes out of the box when you install your execution environment. But yeah, that's a great question. You can also control the size of the pool programmatically by creating a ForkJoinPool with a parallelism parameter. And this can be used to give something other than available processors. About the only reason you would ever do this is if you want to explicitly limit the number of cores that you want to be included in a given ForkJoinPool. So imagine you had 4 cores on your machine and you wanted to make sure a couple of the cores were available for other things. You might restrict the parallelism in a ForkJoinPool to something less than the number of cores because you want to preserve some for other uses or other programs or something else. So it's pretty common that you would use the default constructor here, not this one. But you can. It gives you the opportunity to do that. You can also access something called the common ForkJoinPool via a static method. And so common pool will give you back the one and only common pool reference. And so you can see here we have a static final ForkJoinPool field called common, and common pool returns a reference to that common pool. So it's a little bit like a singleton, although it's initialized in a slightly different way. But there's only one of these things. And as we've talked about before, the reason for having one of these is to allow global resource management of the number of cores so that you can have the work stealing work on a broader range of tasks. This common pool will be used by any ForkJoin task that's not explicitly submitted to a specific pool. So if you were to create your own special ForkJoinPool, either one using the default constructor or one here that specifically gives parallelism, then you can use that directly to submit tasks to. But if you don't indicate a specific pool, it'll use the common ForkJoinPool, and it'll glom everything into that pool. ForkJoinPool also provides a bunch of helper methods that monitor and manage various characteristics of the pool. One of the methods returns the target parallelism level of the pool. So if you create a pool with four threads, you create a pool with 4 threads with parallelism 4, then getParallelism will return 4. There's also one that's called getPoolSize, which returns the number of worker threads that have started but not yet terminated. That is different from getParallelism because pool size can grow based on various properties that you might set later, things like manage blocker and so on that we'll talk about shortly. There's something called getQueuedSubmissionCount that estimates the number of tasks submitted to the pool that haven't started to run yet. And then the final one, which is actually a pretty cool little helper method, is called getStealCount. And that will give you an estimate of the number of tasks that have been stolen from one thread's work queue by another. And we're going to take a look at this later when we look at some of the example applications, because you'll see that depending on how you do your ForkJoinPool programming, you could have lots of stealing or you could have a little bit of stealing. And stealing in general can be helpful, because when you steal threads, that lets other threads run, and it gets the parallelism to be running more thoroughly, and you can get things to process and utilize the cores more effectively. But depending on how things work, stealing takes some time. So there's just some trade-offs that we'll talk about later. OK, so that's a quick overview of the key methods in the ForkJoinPool. In practice, people often use invoke if you want to start something off and wait for it to finish. If you want to start something off and not wait for it to finish, you can use submit. Execute's not quite as common to use.